Yeah, so today I will present the paper design and evaluation of IPFS. So first, let's explain what is IPFS. It stands for InterPlanetary File System. It's a decentralized storage and delivery network and operational since 2015. It's far from a academic prototype. It's had 1 billion of weekly requests. It serves hundreds of terabytes of traffic and tens of millions of unique weekly users. And this system underpins multiple applications ranging from social media to machine learning to e-commerce. And this is the information I took from the slides. So there are 3 core building blocks in IPFS. There are content addressing, peer addressing, and content indexing. So in IPFS, each piece of content is assigned a unique content identifier, which is generated based on the cryptographic hash of the content. This is a content-based addressing approach, and it helps decouple the name of the content from the storage location. So like in HTTP, a file is identified by the file name and the location where it is stored. So if this file is removed from this host, then you cannot access this anymore. But in IPFS, a content identifier is a string of number and letters, and you can use this CID to fetch the file no matter where the content is stored. This is the structure of the CID. It has 4 fields. The first field is the multi-base, which indicate the encoding, the base encoding of the CID. And in this example, B stands for the base 32 encoding. The next field is the CID version. Can you see my mouse? Can you see my cursor?
Yeah.
Okay.
Yeah, we can.
Yeah, great. So next is the CID version, and there are 2 versions. There are 2 versions of CIDs, version 0 and version 1. The next field is multi-codec, and this identifies how the data that the CID points to is encoded. And this could be like protobuf or JSON, etc. The last field is multi-hash, which is a self-describing hash digest of the data. The multi-hash itself contains the metadata to indicate the hash function that is used. So for example, here it's using SHA-256, the length of the hash and the actual hash of the file. When a file is added to IPFS, it is split into chunks and 256 kilobytes by default. And each chunk is also assigned its own CID. IPFS builds a Merkle-directed acyclic graph or a Merkle DAG over the file. And this a Merkle DAG is here. I'm showing an example. So this the leaf are the hash of the individual chunks of the files, and the inner nodes is the hash of the churn. And with this structure, you can verify the content of the files, because every time the content of the files change, then the root node will change as well. So the content provider will send this Merkle DAG to the content retriever, and the content retriever can use this information to fetch the blocks and verify the content inside the blocks. Similarly, every peers in IPFS is identified by the peer ID, and this peer ID is a hash based on the peer's public key. So when a peer try IPFS, it will generate a public-private key pair, and the peer ID is the hash of the public key. A PID can also be resolved into a multi-address, and this is the actual contact information of a peer. A multi-address is a format that can specify different protocols from the network layer up to the application layer. So for example, here it's identify the IP address at the network layer, the port of the TCP protocol in the transport layer, and the PID in the application layer. To publish and retrieve content in IPFS, it needs a mapping from the CID of the content to the PID. of the content provider, and from the PID of the content provider to the multi-addresses of the content provider. And it does this by using a distributed hash table based on Kademlia. The CIDs and the peers are hashed with SHA-256, so they all share a common 256-bit key space. A peer can either be a DHT client or a DHT server. So now go through the process of publication and retrieval of the content in IPFS. Let's say you want to share a file to your friend. The first step is you import the file into IPFS, and the file will be assigned a CID. Next, your host machine will walk the DHT to find the 20 closest peers. The notion of closeness here is based on the SOAR distance in the Kademlia DHT. And then it will generate a CID to peer ID provider record and push this provider record to these 20 closest peers. After that, you send the CID to your friend, and the host machine of your friend will first ask the already connected peers if they know about the CID, and if they do, your friend can fetch the provider record immediately. Otherwise, your friend's host machine would have to do the DHT walk twice. The first walk is to find the content provider's PID for the given CID, and the second walk is to resolve the PID to the multi-addresses. And once they have this multi-address, they can connect directly to your machine and fetch the content from your machine via the bit swap protocol. The IPFS system also is also complemented with a gateway model. This is for users who have not installed the IPFS software. This essentially offers a HTTP entry point into IPFS, and it's a gateway. The gateway is a bridge between the DHT server and the Nginx HTTP web server. So for example, if you can go to this URL to access the XKCD archive directory, and this is a screenshot of what it looks like in the browser. So to evaluate the system, the authors collected 3 datasets. The first dataset is the peer data, and it covers information about peers acting as the DHT servers. They collect this data by using a crawler running in Germany and gather a list of all peers in the DHT. Periodically, the crawler revisited all previously discovered peers to measure their uptime. The second dataset is the IPFS gateway usage data, and this can be sampled from the traffic in a gateway in the US. The last dataset is the performance data, and they collect this data by deploying 6 IPFS nodes in 6 AWS regions. And then periodically, one node will announce a new 0.5 megabyte object, and the other nodes will try to retrieve this object. In this figures here, it shows the total number of crawl peers over time. The red shaded area here is the time periods where they collect the gateway data. The orange shaded area is the time where they collect the performance data, and most of the analysis is performed in this blue shade area here. So let's look at the geographical distribution of the network. The author found that in the DHT there are almost 200,000 unique PIDs, and this covers 464,000 unique IP addresses, but 45.5% of which was unreachable. The peers span across 152 countries, and most of the peers are in the US and China, with 82.5% in the US and 24.2% in China, and followed by France, Taiwan, and South Korea. Some peers advertise multi-addresses that include IPs that map to multiple countries, and this is called multi-homing, and there are 8.8% of them do multi-homing. Next, let's look at the distribution of autonomous system. In this graph here, the axis is the rank of the autonomous system, and the y-axis is the number of IP addresses in each of the autonomous system. Notice that the axes are in log scale. So you can see that the first 10 to the fourth, the first 10,000 autonomous system hold the most number of IP addresses, and the ones from 10 to the fourth to 10 to the fifth has only around 10,000 IP addresses. So specifically, the peers appear in 2,715 unique ASs. The top 10 ASs contain 64.9% of the IP addresses, and the top 100 ASs contain 90.6%. This means there's a wide geographic spread, but each region is dominated by a small number of ASs. This is resilient in case of severe network fragmentation, but the author found that there is a need to broaden deployment to avoid consolidation in a minority of the ASs. Surprisingly, only 2.3% of the IPFS nodes are hosted in cloud infrastructure. This suggests that the majority of users host their own deployments, and this is important for a decentralized system because they don't want the nodes to be hosted on just a few cloud providers. Then they look at the churn rate, which is essentially the uptime of the rate that the peers go in and out of the network. In general, the uptime tend to be short. 87.6% of the nodes are up in under 8 hours, and only 2.5% exceeds 24 hours. And it also varies greatly based on region. For example, the median uptime in Hong Kong is 24.2 minutes, but it's more than double in Germany. So in the CDF graph shown here, you can see the uptime in Germany is a lot higher than the other countries. So the takeaway from this analysis is that IPFS is widely adopted around the globe. A majority of IPFS users run nodes on personal or on-premise commodity hardware. However, this contributes to the high churn rate. More than half of the peers reside in a minority of autonomous systems, so which is something that should be addressed. Next, we look at the performance numbers. This is a performance for content publication. The overall publication process take around 30 seconds for P50, 112 seconds for P90, and 138 seconds for P95. If you look at the graph over here, down here, the overall publication process does not vary by region, and it is dominated by the DHT walk to find the closest 20 peers that we hope to provide a record. Next is a content retrieval performance. They found that the success rate was 100% during their test, and the overall publication process took around 3 seconds for P50, 4.3 seconds for P90, and 4.7 seconds for P95, which is much lower than content publication. Note that these numbers include the opportunistic content discovery timeout, and in the experiment, all of the files are new, so the neighboring peer doesn't know about the file yet. So this content discovery would time out after 1 second, and so unlike HTTP, this also include lookup time, which is the time to figure out which host is holding the content. In contrast, in HTTP, the URL already have the encoded locations, and there are a lot of variations across regions. So you see here in the graph, in the EU regions, the latency is much lower than the latency in Africa and Asia Pacific region. Finally, is they evaluate the performance of the gateway. And this graph here show the size of the files that being loaded from the gateway in green line, and the latency of the gateway in red line. 79.1% of the retrieve object are about 1 kilobyte. So this part of the so 79.1%, and you see you can see that the red line start from 46%, which means 40% of the fetches have a latency of 0, and this is because the gateway also cache the files in the Nginx server, which help with the latency if the cache is hit. The other 38% of the fetch have less than 8 milliseconds. And this is because they also use another cache in the IPFS host. So this part from here to this dotted line is the hit to the cache in the IPFS host, and the rest of the requests would go to the IPFS network. So the takeaway from this performance evaluation is IPFS achieves shorter retrieval delays, only a few seconds, as compared to prior DHT deployments. Like in BitTorrents, the median lookup latency exceeds a minute. Publication delays are higher than retrieval delays due to the need to push the provider records onto the 20 distinct peers. And the retrieval delays are still slower than HTTPs. And this is something that the author felt that would need more improvement. Also, the use of the gateway substantially speed up the retrieval thanks to caching. And that's all I have today. Thank you.